Hello again, everyone. It's your friendly heavy physics teacher here with another video lesson for this time just for the college physics kids because of the way I have to cover this particular part of waves with them. All right. Now, for you college physics folks, this is Unit 10, Lesson 5.1. Okay. I'm breaking Lesson 5 up into two parts uh, so that I can cover um, waves on a string and harmonics in a separate part. But you should already have the notes for everything that we're covering with Lesson 5 and toto. Uh, Today we're just going to talk about wave interactions where we have boundary effects or interferences. Okay, and what we mean by the two of those I'll get to in just a moment. Okay, we've described waves. We've talked about wave characteristics, speed, wavelength, frequency, period, amplitude, and we talked about the fact that in a single medium, the speed of the wave remains constant. In a single medium, the speed of the wave remains constant. Well, two things can happen with that. All right. One, the wave gets to the boundary of the medium. What happens when that wave gets to that point? Two, what if it's wiggling through the medium and another wave wiggles through the same point? All right. What's going on? All right. So those are the two situations we're going to look at today. What happens when we encounter that boundary at the edge of medium and it becomes something else? For instance, there is a boundary between a vacuum and material, and it's called the atmosphere. All right. That boundary, the thickness of that boundary to the distance that light has traveled from the sun is actually quite short, and it's quite a quick boundary, especially to the speed of light. Okay. But to sound, no, that's not a dramatic boundary. Yet within the atmosphere, when you have strong variations in temperature, you can create boundaries of air masses that will change how sound moves through them. In the same way in the water, differences in the salinity of water can cause sound waves to change how they'll move through the water. Even though it's still water, how the salinity in the water, how the temperature in the water is, will change how water will affect the behavior of sound waves moving through it. Okay? And so all of this is, we're going to give you a basis for the exploration that you might need to use in the future in those circumstances. Okay, wave interactions. All right, what do we mean by wave interactions? There's two possibilities here. Okay, one is the wave encounters another wave while it's moving through a medium. Okay, so that is one form of wave interaction, and we call that interference. Wave interference is the phenomenon of interaction when a wave encounters another wave in a medium. Okay. The second type of interaction is what happens when a wave encounters a boundary or a very, very strong, a dramatic change in the properties of a medium. Okay. That can act as a boundary. All right. A dramatic change or a strong change in the properties of a medium can create a boundary effect similar to if we went from water to air, air to glass, water to glass, for different kinds of waves moving through those mediums. Okay? All right. Now, I want to make a particular point here. The first interaction we're going to look at is wave interference. What happens when one wave meets another as it moves through the medium? Okay, and so two waves are passing through a medium. They could be going in opposite directions. They could be going crosswise to each other. Even if they're going in the same direction, If I have two different kinds of waves, but they're similar in qualities, they might actually create an interference, okay? But if they were both sound waves and they were traveling in the same direction, one sound wave would not meet another sound wave. Why? Because all sound moves the same in the same medium, okay? Doesn't matter what the frequency is, doesn't matter what the wavelength is, all sound moves at the same speed. So if you say something and then attempt to say something after it in a higher tone of voice, it's not going to catch and overwhelm or interfere with what was said before. If two people are speaking, they may you may have a hard time discerning what they're saying because the interference is creating that clash of voices that you hear. But if one person starts speaking and another person starts saying the same identical words a moment later, you're going to hear what you think would be an echo, but it's not, because the one person's words aren't catching up with what the first person said. All right? So, wave interference is the effects on the amplitude of a wave in a medium when another wave passes through it at the same location. All right? So two waves going through the same point in a medium at the same time, their effect on each other is to change the overall amplitude of the motion of the medium. Let me say that again. When two waves interfere at a point in a medium, their overall effect is on the amplitude of that point in the medium. Okay? It's not going to change the frequency of either wave. It's not going to change the period of either wave, but it will change the amplitude that each wave is providing to that point in the medium. Now, another important thing you have to remember about this. Waves pass through each other. They do not bounce off. And this is what makes waves so different from matter. Imagine, if you will, in front of me, I have a billiard table, okay? And on one corner over here, I have a hopper full of green billiard balls. And over here, I have a hopper full of red billiard balls. And I send them down from those hoppers and they make a line and they're going to meet at this point right here. Okay? We know that if they are normal Newtonian billiard balls and the green ones are going this way and the red ones are going this way, that they're going to hit and they're going to bounce. Okay? And so going off in this direction, you would see green ones. And so if I had a collector over there, it would be a basket that would collect green billiard balls. Okay? And with the hopper sending the red billiard balls this way, they would hit and they would bounce and they would go off in that direction. And you'd have a hopper over there that would be collecting red billiard balls. And as long as the mechanism for releasing the stream of billiard balls releases them at exactly the same moment, chunk, they both go out, they'll knock and come off. Okay? It's only if you got this kind of a malfunction here that you'd get a crossover. And we're not going to deal with that. All right? The mechanism is perfect. It releases a set of billiard balls. They go out and they'll knock off. Come next set, knock off. They would never get released so that they wouldn't be meeting at that point identically. Okay? Now, instead, imagine that I had a green flashlight here and a red flashlight here. And I shine those two so that the beams cross right here. Okay? What color would you expect to see over here on a screen in a hopper? All right? Green started over here. Is it going to bounce off and go that way? And the answer is no. because this is the phenomenon of wave interference. Waves are energy. They will pass through each other. They will not bounce off. And that's why, folks, much as I would love to have lightsabers, the way they work in Star Wars is just really bad science. The lightsabers would pass through each other if they were truly light and energy. Nope. All right, George Lucas. What were you thinking about? I mean, lightsabers are cool and all, but as fencing duels, they pass through each other. They pass through each other. Wouldn't work. Okay? Light passes through as it interferes. It does not bounce off. Okay? All righty. So what happens at that interference point? All right? If we've got the light beam going out and we got the other light beam going out, what's happening over here at this interference point? Well, if the amplitude of each of the light beams, or the amplitude of two sound waves, or the amplitude of two ocean waves, or the amplitude of two earthquake waves is in the same direction, we're going to get something called constructive interference. Okay? And constructive interference is when two waves have the same direction for their amplitude. Their amplitude, the interference is the vector sum of their amplitudes. So if the vectors are in the same direction, it's simple addition. Okay? So here I have a very simplified version of constructive interference. Okay? Let's say we have a wave pulse and it's moving to the right, and we have another wave pulse and it's moving to the left. Okay? And they are going to meet at some point in this medium, which let's call it a string. All right? And so this wave pulse moving that way, this wave pulse moving that way. Notice that the amplitude for this one and the amplitude for this one both are vertically upward. Well, when they meet, that moment, that instant of meeting is called the superposition. And the superposition is going to have an amplitude that is the vector sum of the two waves. And in this case, since both of the waves are equal, well, it's just double their sum. Let's say that the blue wave was +2, where the green wave was only +1. Over here, the amplitude for A would be +3. +2 if the blue were +2, +1 if the green were +1. Amplitude would be +3. Okay? And then this only happens for a moment in time. It's really quick. All right? It's not like it's going to sit there and wiggle there and show you that a superposition has occurred. You'll get this momentary moment where the two waves, if these were sound waves, you would hear it louder here for a moment. If these were light waves, it would be brighter here. If these were ocean waves, well, somebody riding the ocean here would go up and down a little bit, but over here they go up and down a lot. Okay? And then later on, we'd notice that the two waves would continue on in the direction they were originally traveling. Pass through each other. Pass through each other. Okay? Well, what happens if the waves are in opposite directions? What happens if one amplitude is up and the other amplitude is down? Remember, it's a vector sum. And because of that vector sum, when the amplitudes are in opposite direction, it's essentially a subtraction. Okay? So let's say our wave pulse this time, we've got the green pulse moving to the right, we've got the blue pulse moving to the left, but this time, this is a positive amplitude, that's a negative amplitude. When they meet, you don't actually see the green or the blue. What you see is the fact that the medium stopped moving. Here, the medium is up, the medium is down. And as they cross, the medium is kind of not doing anything. You'd see the green one shrink as it entered this point. You'd see the blue one shrink as it entered this point, and for an instant in time, it would flatten. And then all of a sudden, you'd see the green rise out. You'd see the blue rise, well, fall out, if you want. Okay? And they would continue on. The green would continue on to the right, the blue continuing on to the left. Okay? Again, it's a vector sum. If the green happened to be +2 and the blue happened to be -1, I would get a lower hump over here that would only be +1. Okay? Because this +2 plus a -1 vector sum, a -1 gives me a +1 amplitude for the medium. Okay? Constructive interference. The amplitudes are in the same direction, so you get a regular addition. Destructive interference, you get amplitudes in opposite direction, and so you get a decrease in the amplitude of the medium at the superposition. Okay? Now, what happens when we get a continuous wave meeting another continuous wave moving through the medium? Well, that creates a very interesting pattern, and that pattern is known as a standing wave. All right, a standing wave. Standing wave can happen in one of several ways, all right? But what it is a stationary pattern of constructive interference superpositions. These are called antinodes. And destructive interference superpositions. Those are known as nodes. So let's say I've got this wave, this blue wave moving that way, moving to the right. It encounters a boundary, a hard boundary in the medium. And so that causes it to reflect back on itself. And in reflecting back on itself, it reverses the amplitude of the reflected wave at that point. So if it's down here, it's going to start rising over here. All right? And so what we get is we end up with these locations, and I'm going to draw this, well, point this out right here. Okay? This right here, where we'd see it go down, and then we'd see it come up, and we'd see it go down, and it come up, but it would appear to stay there. It would not appear to move across the space anymore. We wouldn't see anything coming back. All we'd see is this wobbling up, down, up, down, up, down, up, down, up, down. Okay? This place in between these points represent where there would be destructive interference happening. And that destructive interference we call a node. The constructive interference we call antinodes. And if the antinodes and nodes do not appear to be traveling from one point to another in the medium, then we've created what's known as a standing wave. All right? There's lots of different ways of creating this. This is one example where the waves bounce off onto themselves, and then that pattern that's created would be a standing wave within that place where they are bouncing off and interfering with each other. Okay? Now, what do we call bouncing off the boundary in between mediums? That's known as reflection. Okay? So, reflection, the bouncing of a wave off a boundary or part of the wave's energy off of a boundary between mediums. So for instance, let's say we have a light wave and it's passing through the air on the way to a window, all right? And so inside the glass of the window, some of that wave energy is going to go through. But we all know that you can see a reflection of yourself in windows. So that means that if you're standing in one place and your friend is standing over here, they could see their reflection of you. Okay? Or you could see their reflection on the way back. Okay? So the wave energy is coming in, it's a certain wavelength, it's going to hit that boundary. Some of it will go into the new medium. We'll talk about that on another day. But the rest of it bounces off. Okay? And so this is what we call reflection. All right? It can happen straight on, it can happen at oblique angles. The interesting thing that's going on here is we have to measure our angle of incidence and our angle of reflection. We do not measure it from the boundary. We always measure it from a normal line to the boundary. So that would be what we call our angle of incidence. This over here is our angle of reflection, okay? And for any sort of reflection, the relationship between those two is that the angle of incidence is always equal to the angle of reflection, okay? But you always determine it from a normal line to the boundary, meaning a perpendicular line to the boundary, all right? All angles that we deal with based on the path of a wave compared to a boundary in the medium, we have to measure those angles from a normal line to the boundary, not from the boundary. Okay? All right. That's what I want to cover for right now, and that's why I'm calling this lesson 5.1. All right. Now on the notes, you'll see that that reflection part came first, and then I talked about interference, and then it talks about waves on a string. That's for another day. All right. What I want you to take away from today: one, when waves are moving through a medium and they encounter another wave in that medium, that encounter is called interference. It can create a pattern which appears to be stationary, where if the wave's amplitudes are in the same direction, it creates constructive interference. If the wave's amplitudes are in opposite direction, it creates destructive interference. The constructive interference are called antinodes. The destructive interference is called nodes. And if those antinodes and nodes appear stationary to an outside observer, we call it a standing wave pattern. Okay? Reflected waves can create standing wave patterns as the incoming wave interferes with the outgoing wave. All right? And in that V that's in between them, it can create a standing wave pattern where you get nodes and antinodes as the incoming wave and the outgoing wave are interfering and creating nodes where it's destructive interference and antinodes where it's constructive interference. Okay? Interference is the vector sum of the amplitudes of the waves passing through that point. The point of interference is called superposition. Alrighty. And reflection, all our angles for reflection have to be measured from a line normal to the boundary. In other words, a line that is perpendicular to the boundary. Don't measure incident angle, reflected angle. Don't measure them from the boundary to the path of the wave. Measure them from the normal line to the path of the wave. Alrighty? If you have any questions, remember to contact me by email. Let's see. Anything else, I'll be getting to you with email. Thank you very much. Have a great day. Have a great afternoon whenever you're viewing this. Great evening whenever you're viewing this. And hopefully I'll see you sometime soon. At least not till 29th anyway. Bye-bye.